Hello everyone, I'm Yuchen Chen from Shanghai Jiaotong University. In this talk, I'm going to share about our work, OPS, Optimized Shuffle Management System for Apache Spark. This is a joint work with City University of Hong Kong and Intel Corporation. Since MapReduce, distributed parallel computing frameworks, such as Apache Hadoop and Apache Spark, have been rapidly developed and widely deployed to process the exponentially increasing data for numerous applications. Spark uses resilient distributed dataset, or RDD, as the basic abstraction. A job is divided into several stages according to the data dependency in Spark. The many-to-many data transmission between stages is called shuffle. In the internal implementation of Spark, the output of map subtasks is divided into multiple blocks according to a partition function. As the reduced subtask starts and enters the shuffle phase, the reduced subtasks will issue shuffle requests to various nodes based on the data dependencies. After Spark receives shuffle requests, it reads and transfers a small part of the intermediate data file based on the offset in the index file. To study the resource utilization of the shuffle phase, we ran a Spark application of sorting with an input data size of 512 gigabytes. At the end of each round of the map subtask, there is a large number of intensive disk I/O, while the network I/O resources are entirely idle. After the reduced subtask starts executing, they first enter the shuffle phase and begin to perform many-to-many data transmission. There is a network I/O peak because all reduced subtasks enter the shuffle phase and start data transmission at the same time. Many studies have shown that simultaneously establishing a large number of many-to-one TCP network connections and transmitting a large number of data reduces network I/O performance and may cause TCP encast problems. It can be seen that there is a peak shuffle request after the start of the shuffle phase, followed by a significant trough. We discovered that the root cause of the above situation are as follows. One is due to the resource slot-based scheduling method that does not consider I/O resources. The other is due to the calculation logic that couples data transmission and calculation. The number of execution runs of a computing task is determined by the number of input data blocks and framework-related configurations, which can be adjusted before the computing task starts and is recommended to be at least twice the total number of CPUs. However, since the shuffle phase is coupled to the reduced subtask, although the intermediate data of the first 3 rounds of the map phase have been persisted on the local disk, the network transmission during the shuffle phase still has to wait until all map subtasks are finished before they can start to gather. Previous studies have shown that dividing a computing task into a large number of subtasks to be executed in a cluster can help improve the parallelism of computing and reduce the performance impact of stragglers. However, when running actual big data processing applications, if too many execution runs are allocated, it causes a considerable performance overhead in the shuffle phase. To verify this drawback, we ran the same 512 gigabytes two-stage sequencing application on Spark and increased the number of subtasks from 640 to 6,400. We discovered that as the number of subtasks increases, the total execution time of the shuffle phase increases sharply, and the cost of the shuffle phase starts to increase after 3,200 subtasks have executed. And the number of shuffle requests grow to the power of the original, while the amount of transmission for each shuffle request also gradually decreases as well. Many previous studies focus on optimizing the I/O requests. Selfish and Rifle both merge the intermediate data files and use batching processing to reduce the I/O requests. However, Selfish needs to modify the current file system and suffer from stragglers, while Rifle still suffers the intensive network I/O and may result in TCP incast problem. Other studies focus on optimizing the workflow of Shuffle. iShuffle separates the shuffle phase from the reduced subtasks, but I/O resources cannot be efficiently used. Xcache implements in-memory shuffle management with pre-scheduling. However, Xcache is only available when the size of dataset is lower than memory and lacks the support of fault tolerance. Based on the observation and some existing optimizations, our goal is to design an optimized system that breaks the synchronization barrier in the shuffle phase, mitigate the number of shuffle requests with more practical workload, that is, larger than memory data input, and improve the utilization of our resources. Our solution is called OPS, an optimized shuffle management system. This is the basic workflow of our design, and it is mainly divided into 3 phases. First, early merge phase. In early merge phase, the map subtasks do not apply the partition function to the calculated intermediate data, and the unprocessed intermediate data is directly transferred to the shuffle handler of the ops worker node through shared memory. Only one ops worker node runs on each physical node, and the output of the map subtasks in all Spark executors on this physical node is transferred to the same shuffle handler. Subsequently, shuffle handler transfers the collected intermediate data to merger for early merge. Second, early shuffle phase. In early shuffle phase, the early merge data is not be stored on the local disk, but is directly transferred to Shuffler for early transmission. Shuffler interacts with the scheduler in the OPS master node and obtains assignments of subtasks in subsequent stages. The scheduler on the master node uses a particular strategy to predict the data distribution and assign subsequent subtasks to notify Shuffler for early transmission. Subsequently, Shuffler transfers the merged partition data in advance according to the obtained subtask assignments. Finally, local fetch phase. In local fetch phase, data manager receives the data transmitted in advance and stores it on the local disk to ensure fault tolerance. The reduced subtasks request the partition data from a shuffle handler with the partition number as a parameter. After confirming the transfer is completed, it returns the position of the partition data on local disk. The reduced subtasks pull data directly from the local disk instead of pulling them from the remote. Next, I'm going to introduce our main optimization strategies: early merge and early shuffle. The merger of ops collects unprocessed intermediate data from the map subtasks by shared memory and uses a partition function to partition data and store it in memory. During the early merging of ops, all operations are in-memory operations, and no data is written to disk. Ops has this memory management module and allocates memory space in the heap of JVM to store data. We use an object called partition page to store intermediate data. A partition page is essentially an array and has basic attributes such as number and size, and is only used to store the data of the same partition. After the partition page is full, it is added to the partition queue, waiting for the next stage of early shuffling. Merger maintains the same number of partition queues as the number of partitions. The scheduler of ops performs early scheduling based on the partition data of the first round of map subtasks and starts early shuffle after the memory usage reaches a certain threshold. Ops releases memory resources after the early shuffling of the partition page is completed. The early merge strategy avoids the intensive shuffle requests in the original shuffle phase. The transfer module of shuffler is responsible for point-to-point intermediate data transmission. Ops executes early merging and early shuffling in parallel. When the storage memory usage reaches a certain threshold, Ops triggers early shuffle, which transferring the data in memory to the partition node according to the partition queue. Compared to the original Spark, Ops advances the entire shuffle phase to the beginning of the main phase. The early shuffling of Ops breaks the synchronization barrier of the BSP model. During the early shuffling, transferer reads the partition pages in different partition queues in turn for transmission as a consumer. Transferer continues to transmit until all corresponding partition queues are empty. Users can set different trigger thresholds for tuning based on network bandwidth and memory size of the cluster. The execution of the early shuffle policy of Ops depends on a critical piece of information: the scheduling results of the reduced subtasks. In the original Spark calculation logic, the shuffle phase and the map phase are executed sequentially. Ops implements its own subtask scheduler, predicting the partition data distribution and early scheduling. When the reduced phase of Ops is triggered, Ops notifies the resource shuffler of Yarn of the results of early scheduling, and force Yarn to allocate reduced subtasks according to the results. The scheduler of Ops predicts the final partition data distribution by the early merged partition results in memory and performs early scheduling based on the partition results. Ops is designed to trigger early scheduling in the following two cases. The first is when the first early shuffle is triggered and when the number of completed map subtasks reaches the set threshold, according to the result of early scheduling. If the storage memory of Ops is fully allocated, early merge will be blocked, leading to the calculation of all map subtasks block. So when the memory usage reaches the threshold, Ops proactively triggers early shuffling to avoid the mentioned situation. Our experimental environment was built up on Amazon AWS EC2, and we rented 100 T3.xlarge nodes with a 4-core CPU and 16 gigabytes of memory to form a testing cluster. We deployed Hadoop Yarn version 2.8.5 and Spark version 2.4.3 on the cluster and allocated 10 gigabytes of memory for early merging. We used the native random text writer of Hadoop to generate 1.6 terabytes of random text, which is divided into 1,600 to 6,400 copies and stored on average on nodes of HDFS. The number of parallel subtasks is set to 400. So the number of subtasks execution runs for each stage is 4 to 16 runs. The amount of data processed by each subtask is 250 megabytes to 1,000 megabytes. And disk overflow was not triggered in each stage. Ops fully utilize the throughput of the disk and the network resources, and the total execution time of the application is optimized by 41%, and the execution time of reduced by about 50%. Ops outperforms original Spark and Scache in our resources because of the early merge strategy and the improved early shuffle strategy. For network IO resources, Due to the larger memory workload and all nothing constraint of Cache, the intermediate data is stored on the local disk, the same as the original Spark. While with ops, the subtasks in the map phase are only responsible for reading the data for calculation and release the resources after transmitting the output to ops. Ops also early merges the intermediate data so that the large enough data size can fully utilize the resources. So disk I/O resources with the original Spark, such a large amount of random and small disk I/O have reached the disk I/O bottleneck, which severely slows the completion of the reduce phase. As cache reads fragmented data block files for the local disk during the reduce phase, which causes a large amount of random disk I/O, and it cannot fully utilize the disk throughput. While with ops, the reduce subtasks directly read the intermediate data from the local disk after communication with ops, and read and write sequentially. Next, we pay attention to the completion time of a solved application with different numbers of subtasks. After using the shuffle service of ops, the end-to-end completion time of the task is reduced by 17% to 41%. In addition to the optimization of the reduced phase, the completion time of the map phase is also steadily reduced, which benefits from the independent shuffle service provided by ops. The map subtasks do not wait to write data to disk after the calculation is completed, but directly transfers it to ops through shared memory. The map subtasks can release resources to the next round of map subtasks after the data is transferred. To verify the usability of ops optimization effect, we use various data tests of HiBench to evaluate the performance of ops. We can discover that in addition to word count and page rank, ops optimized Spark can achieve excellent performance optimization. This is because word count and page rank are not shuffle-intensive jobs due to the characteristic of the workload. In the shuffle phase, the execution time accounts for many more applications in the total execution time, and the optimization effect brought by ops will be better. To conclude, we introduced ops, an optimized shuffle management system for Apache Spark. Ops is built up on three main techniques as follows. First, ops early merged the intermediate data from the map subtasks into memory with a unit called partition page. Second, ops uses an early scheduling algorithm to predict the final partition distribution based on the regression model built by the partitive partition data stored in memory. Third, ops early shuffle the merged intermediate data to the target nodes based on the result of early scheduling, breaking the original synchronization barrier. Overall, ops optimizes the overhead of the shuffle by nearly 50%. In the test cases of HiBench, ops improves end-to-end completion time by nearly 30% on average. Thank you for your attention.